I'm Samir Menon, and this is joint work with David Wu. We present Spiral, fast, high-rate, single-server PIR via FHE composition. So in private information retrieval, a client wishes to retrieve an item from a database without letting the database learn which item they're retrieving. And specifically, this guarantee should hold even when the server is arbitrarily malicious. You can imagine as a motivating example, the client wishing to retrieve an article about a sensitive medical condition from Wikipedia, say. Our focus is the single server setting because it is a basic building block in many other privacy-preserving protocols. I've listed some here. You can also imagine, like just to call out, like private DNS as a motivating example where the client would like to look up a DNS record without letting the server know which record it's looking at. When evaluating a PIR system, there's a number of efficiency metrics that we want to look at. The first is the size of the query. So this is how much the client needs to upload to issue a query. The second is the server throughput. This is the rate at which the server can process the database to answer a query. So remember that the server, without pre-processing, needs to perform a full linear scan over the database in order to answer a single query for privacy. So we measure the server's response time as throughput. And finally, the rate. So this is a kind of crypto word, but basically the rate here we refer to as the ratio of the record size to the response size. So the response is typically somewhat larger than the actual item, the size of the item that you're trying to retrieve. So that blow up, the inverse of that kind of response overhead is the rate. There's a fourth metric that we kind of call out, which is the public parameter size. So the client is allowed to send a set of public parameters to the server at the start of the session, and these parameters are reusable for an arbitrary number of queries and on an arbitrary number of databases. But the size of these parameters is still important because the client has to upload it and the server needs to store it. So we also measure the size of these parameters. So just a summary of our results, we introduce a family of PIR protocols that leverage techniques to translate between FHE schemes, and we achieve significant new results in single server PIR. We use automatic parameter selection based on the database configuration to choose parameters for our scheme, of which there are a lot to choose. And ultimately, this lets us achieve significant simultaneous improvements in query size, rate, and throughput over the best state-of-the-art prior. But in exchange, our public parameters are larger. So you can see here, I've listed, we are improving on all three key metrics, but the public parameters are getting larger. And we also examine Spiral in a streaming setting. This is where the query from the client is fixed, but the database is changing. So we have multiple databases, and we'd like the answer to the query on all of those databases. This comes up when you're streaming like a large file, or in other cases that I'll describe later. But basically, in this setting, we achieve much higher rate and throughput, and that's because we use larger queries. We achieve a rate of 0.81, which I'll call out. Remember that the highest possible rate would be 1. So in this streaming setting, we're achieving very, very high rate. And in addition, we're also achieving a throughput of almost 2 gigabytes per second, which is 12 times higher than the previous work, the best previous work. And I'll just call out, on this target system, the throughput of running software AES is 5 times slower than this. So we are significantly faster than applying a symmetric primitive. And for reference, the memory bandwidth of the system is 10 gigabytes per second. So we're a decent way of the way there. So now I'll talk about how does Spiral work. To do that, I need to kind of explain a little background on fully homomorphic encryption. So just to summarize, a client can use homomorphic encryption to encrypt data using a secret key, send it to the server, and the server can then perform operations on that encrypted data. I've listed some here. You can look that the first two are kind of similar. This is ciphertext addition or plaintext multiplication In a way, these are the same, but basically the server can evaluate an additive homomorphism for both of these. And there's also the possibility that the server could evaluate a multiplicative homomorphism. That's where you are taking two ciphertexts and computing a new ciphertext that encodes the product of the two inputs. Anyway, the server sends back this final response, and the client can decrypt to obtain the result of the computation. And here, for fully homomorphic encryption, we have the same definition of rate. So rate is the ratio of the plaintext size to the ciphertext size. So the rate of a homomorphic encryption scheme is very similar to the rate of a PIR scheme. So this work is about composing FHE schemes. So I'll describe two schemes to you. I won't get into the details of exactly how they work, but I want you to just know the properties, and we can see the construction from that level. So the first scheme that we use is Regev's encryption scheme. This scheme gives us very high rate and has very fast operations, but it only supports an additive homomorphism. So you can only add or multiply by a plain text. And it comes in a matrix variant, which is also called PVW. And the thing I'll call out about the matrix variant of this scheme is that the rate is much higher than for the scalar variant. And the rate is higher the larger the matrices that we encrypt. So this matrix variant lets us encrypt matrices, and the bigger the matrices we encrypt, the higher the rate of the resulting ciphertext. And the second scheme we use is Gentry-Halevi, or GSW, and this scheme is kind of the opposite. So the rate is low, the operations are slower, but we support homomorphic multiplication. And interestingly, these two schemes, they play nice with each other. So you can multiply a GSW ciphertext by a Regev ciphertext. So I'll talk about two prior works that use those two schemes to construct PIR. So the first prior work is Gentry-Halevi. In this work, the query is a collection of matrix Regev and GSW ciphertexts. And what we do to start is we use the Regev ciphertext to select along the first dimension of the database. So the database is a matrix of plaintext records. And here I've shown, as an example, I've marked the target item in a star. And we're doing a vector matrix multiplication. So we are intuitively, we're selecting a row of the database in this picture. And you can see we're exploiting the fact that Regev ciphertexts support a ciphertext plaintext homomorphism. So that's how we're able to select a row using these encrypted bits. And then we can further compress the response size using the GSW ciphertext. So here we exploit the fact that GSW supports ciphertext multiplication to basically repeatedly fold the output of that first processing until we're left with basically just a single ciphertext that encrypts the item that we wanted. And so this result is a matrix Regev ciphertext in this prior work, and so it's a very high rate. So we've kind of used both schemes well. I should note this scheme was never implemented, but it seems like it would be efficient, but there's a big drawback, which is that these GSW ciphertexts that you have to communicate are very large. So the query becomes quickly too big. Each ciphertext is, in this example, 4 megabytes, which is to encrypt a single bit, which is a lot. So that's a significant downside. There's another prior work that addresses this downside. So Onion PIR, a recent work, shows how to make the query much smaller. So here the query is only 64 kilobytes, and it's a single scalar ciphertext. And then they show an expansion procedure that lets you get the ciphertext you need for processing. So this expansion procedure works quite well, and you're able to process the query much like Gentry-Halevi, but the query is now much smaller. But there's a problem with this prior work too, which is that the result is now a scalar Regev ciphertext. So the expansion procedure that they show only goes from scalar to scalar. And so the drawback is that the use of scalar ciphertext ultimately reduces the rate. And so we don't get that very high rate that we have in the other prior work. So this work is about getting the best of both worlds. What we want are the small queries that are in Onion PIR, and we want the high rate that's in Gentry-Halevi. And so to do that, we introduce simple key switching techniques for query compression. We show how to basically convert scalar Regev to matrix Regev and convert matrix Regev to GSW. The high-level takeaway is, you can get the benefit of really large ciphertexts without the overhead of actually communicating them on the wire. And our techniques are of general use. So if you use matrix forgev or GSW ciphertext, this transformation is useful and can minimize communication costs. So this is applicable outside of PIR. So this is our final vanilla version of our scheme. On the left here, you can see this looks like onion PIR. What we're doing is we're taking a very small query and expanding it into matrix forgev and GSW ciphertext that we need. And then on the right, it looks like Gentry-Halevi. We're processing the result using matrix ciphertext, and so the rate is high. So this is us getting the best of both worlds. I'll talk about 3 little additional tricks that we use in this scheme. There's more details in the paper, but I just want to call them out. The first is that we choose parameters automatically. So as you build these schemes, there are just an explosion in the number of knobs that you can tune. We wanted to choose our parameters systematically, so we built a tool that takes in the database configuration and then evaluates many sets of parameters against a cost model. In this case, we use the AWS cost model. So what happens is we input parameters and we guess the query size, response size, and the amount of time the server will take to compute a response, and then we calculate a cost from that. And the tool is able to output an optimized set of parameters. There are 2 other tricks. So another trick we use is we choose our ciphertext modulus kind of carefully to use so that we can only use 32-bit multiplication for most of processing. This is actually a big win, especially when you remember that using SIMD like AVX512, you can do up to 8 32-bit multiplications in a single CPU cycle. So this is actually a significant win. And then we also observe a kind of fact about matrix ciphertext. We basically observe that a large portion of a matrix ciphertext is less important than the other parts of it. And so you can more noisily encode it, you can more roughly encode it. There's more details on that in the paper, but that is also of general interest. So the question you're all here for, how does Spiral perform? On a basic level, if we choose the database configuration preferred by Onion PIR, 2 to the 18 records, so that's 250,000 plus records of 30 kilobytes each. Spiral is a significant improvement over the prior work, but has larger public parameters. And you can see on an absolute basis, the query and response sizes are getting pretty small, and the server compute is also getting pretty small. So we think this is putting PIR in striking distance of being practical. And just phrasing those same numbers as rate and throughput, you can see the rate is now already over 1/3, and the throughput is over 300 megabytes per second. We also compare Spiral against comparison schemes over varying the number of records and keeping the record size constant. So here I've chosen 100 kilobyte records, and I've varied the number of records. The first thing to note is, indeed, processing is linear in the database size, especially as the number of records increases. You can see there's, almost all of the schemes become aligned. And another thing to note is in the top right, Spiral is getting over 300 megabytes per second of throughput, which is already roughly the speed of the throughput of software-based AES on the system. When I say software-based, I mean, not using hardware acceleration. But what that means is, this PIR processing is similar to applying a symmetric primitive. And that's kind of an interesting benchmark, we think. It's not on this slide, but Spiral also does have smaller queries and response sizes than all of the schemes pictured here. But it does have larger public parameters. And I should note all our measurements are on a single core, single thread. This is because the problem's naively parallel, so for benchmarking, we always use a single core. So now I'll talk about analyzing Spiral in that other setting, the streaming setting. So in this setting, the same query is reused over multiple databases. And you might ask, when would you ever do that? And the answer is actually, more frequently than you'd expect. So the first time is, if you're streaming a video, you want the database item in chunks progressively so that you can, stream. So that's an example. And another example where this streaming setting comes up is when you're doing a private messaging or a metadata private messaging or voice call system. So here you are repeatedly polling the same mailbox, and so the streaming setting applies. In this setting, we only want to minimize the online costs. We only need to minimize the response overhead and the server compute time. And in return, we can consider larger public parameters or query size because these are amortized over the entire lifetime of the stream. And so it's okay to have a much larger query because the stream is presumably has a long lifetime. So our approach, which we named SPIRALSTREAM, is basically make the query very large. And so that's what we do, and we measure its performance. So here I've plotted SPIRALSTREAM's performance in purple, and you can see that this is much faster already than Spiral. So you can see that by making the query much larger, here the query is 30 megabytes, the throughput that you're able to achieve is much, much higher. And this peaks at over 1.5 gigabytes per second, which is 7 times faster than previous constructions. And as a note, at this point, the rate is about 50%. So the communication overhead here for single server PIR is already, in this setting, only 2x. And it was previously 4x with the best previous scheme. So a natural question we ask next is, okay, it's at 50%. Can we make the rate even higher? So we also think, we kind of reflect back on our scheme and ask, can we make the rate higher? So using larger matrices does make the rate higher, but it lowers the throughput. So the idea for a packing transformation is to use a small ciphertext during processing and pack into a large one at the end. And so we do that. It gives us larger public parameters, but better throughput. And I'll just say, so just to call out here, the cost of privately streaming a movie from a database at this point in settings where the communication is dominating cost is less than 2x more expensive than the no privacy baseline of just directly retrieving the item. And previously that would have been 17 times more expensive. And we have a cool demo of the scheme too. The goal of the talk is to convince you that PIR is practical. So we actually have a website up where you can actually read Wikipedia using PIR. Yeah, it achieves pretty good results. Don't tell the attack people about the URL. But yeah. And yeah, here are some future directions we're looking at and our demo paper and code.
Thanks for the great talk. Any questions?
Yeah, I wanted to ask about these public parameters. Are they truly public in the sense that the generation procedure is public coin and different clients can use the same public parameters?
The generation procedure is not public coin, so it depends on the client's secret key. But of course, it is hiding of the client's secret key. So,
Okay,
yeah.
that makes a lot of sense. And then actually another question. I'm curious about the evaluation and how parallelism played a role or didn't play a role in the evaluation.
Oh, sorry, say that again.
I'm curious about the evaluation and how parallelism either played a role or didn't play a role.
Okay. Yeah, so I guess cryptographers we're all lazy. So most libraries and open source implementations that implement PIR that we use to do benchmarking don't use parallelism because you can just write a note in the paper that says, it's naively parallel. So to make comparison consistent, we don't implement parallelism. If you go to our Rust library, it does. So it'll use all the threads it can, and it'll exploit the threads. Yeah.
Gotcha. That makes sense. Thanks.
Yeah.
Please keep the question short. We're a little behind now.
Hi. So you used fairly large record sizes in your database and fairly small number of records. What happens if those sort of flip around and you have many very small, smallish records?
Yeah, it's a great question. So in the example, one of the benchmark databases is 1 million records and 256 bytes each, right? And here what happens is what we do is we just the most efficient thing because of lattice parameters. There is an intuitive or there's an implicit minimum record size. So what we do is we just pack many of the smaller records into a single large record. And this hurts the rate significantly. Obviously, the minimum response size is now, several kilobytes, but it's still very efficient on a throughput basis. And on an absolute basis, downloading 10 kilobytes to retrieve 256 bytes, it might be okay, depending on the circumstance.
Thank you.